Thanks everyone for coming. I surely see a good mixture of experts today present. And our speaker today is Artem Mukhamedzianov, and he'll talk about the mixture of experts algorithm. Go ahead, Artem.
Yeah, hey everyone. Just wanna briefly talk about mixture of expert algorithm, which is kind of popular right now. Um, I used towards understanding mixture of experts in deep learning papers, which you can find in the Telegram chat. Yeah, let's start then. So the first one is like the most important statements and results of the paper that they mentioned in the introduction is that it's pretty obvious, but I want to mention it. It's the first one. Mixture of linear experts performs better than the single expert, but way worse than mixture of nonlinear experts. There are pretty there are plenty of examples in the article, which you can find it. Another one is cluster structure cannot be recovered by the mixture of linear experts. The mixture of nonlinear experts can correctly recover the cluster structure and diversify. It's really important part for this algorithm. The third one, sparsely gated model with two-layer CNN trained by gradient descent. They use it for every expert in this algorithm. Each expert of the sparsely gated model will be specialized to a specific portion of the data, which is determined by the initialization of the weights. And the router can learn the cluster center features and route the input data to the right experts. So the second point and the first one is like the most important and basic things for this algorithm. Um, let's start. So problem setting and preliminaries. In this section, we define the data generation process and set up the context for the binary classification problem that this algorithm solves, where each page is a d-dimensional vector. We have pairs x and y. It belongs to the real number power d um, into the power of patches, and it has two. It's like a binary class. It has like two options, and it's generated from distribution D. Basically, it's our pair, as I mentioned. We have like we need to randomly sample cluster indices, randomly choose a pair of cluster indices. Then we generate some random variables like alpha, beta, and gamma from distributions. Um, and we can construct the input x as p patches. Um, yeah, the kind of important thing here is that our V and C, they are orthogonal, so it means that they are independent, and it may cause some troubles for linear experts, which like those linear experts have some issues with distinguishing between like independent properties. Um, Another important thing, it's feature signal, cluster center signal, and feature noise. Um, center signal let us to distinguish to which cluster our data belongs. As I mentioned in the slide before, um, our agents are, let me show you. Each expert of sparsely gated model will be specialized to the specific portion of the data. And this cluster center signal allows us to understand to which specific part it belongs. Another thing is feature signal and feature noise. It's really important because sometimes for our model, when we train, feature noise can be really strong, even stronger than feature signal. It may cause some troubles for training. I'll mention it in the next slides. Positions of signals and noises are not specified due to definition. As I mentioned, problem strengths of feature noises can be as large as strengths of feature signals. classification problem has an intrinsic clustering structure that may be utilized to achieve better performance. As an example, we have K clusters which belong to omega K. Pair of X and Y belong to omega K if and only if at least one patch of X aligns with CK. If at least one page belongs to CK, it means that our pair belongs to this omega. It allows us to use individual experts and train them on omega K. Um,
So,
Amish,
Artem, one question. There are only two clusters according to your input, or there are more clusters. Does K go from one to two?
no, it's like,
No, not clusters.
um,
Sorry. There are only two. It's a binary classification problem, but you can have many clusters, right?
yes, of course.
Okay,
Yeah.
gotcha.
So a mixture of experts can learn the data cluster structure from the cluster central signals that I mentioned before. If our structure belongs to some specific, like they use these signals to find the cluster where they belong. Importance of the results, focus of the paper that I'm discussing right now is training a mixture of nonlinear neural networks, a more practical model used in real applications. When mixture of experts is trained by variance or gradient descent, we show that the experts automatically learn to specialize on each cluster, while the router automatically learns to dispatch the data to the experts according to their specialty. So these things allows us to receive the most, like, the best, it's like our best case scenario in this model, because we assign some specific task to the best fitted agent expert that can handle this task. Although from a representation point of view, it's not hard to see that the concept task can be represented by mixture of experts. Our result, like the result, is very significant as they prove the gradient descent from random initialization can find a good mixture of experts with the nonlinear experts efficiently.
Mhm.
Um,
But
so
the clusters are not given to the network, right? Sorry, I just want to understand the setup. The clusters are generated by present in the data set, but the neural network doesn't know about it. So somehow it has to learn and understand which expert will
yeah,
learn which
yeah, these
cluster.
clusters they have like normal distribution. Yeah.
Okay,
Uh,
got it.
mhm.
Mhm.
So that's really important formula for the mixture of experts. It's like structure of the, like, the mixture of experts layer. It consists of a set of M. M it's like all our experts that we have in our network, and gate network, which is generally said to be linear. Um, um, just give me 1 second. Um, yeah. X is like our input data. Um, big W, it's the parameters, it's like weights of the expert network of, like, not of everyone, it's like for every expert has their own weights inside their local network.
Mhm.
Um, the output of the M's expert network with input X and parameter W, they define an M-dimensional vector in this way, where x power p, it's pth patch of the input x. We have theta. Theta in this case is a matrix of parameters for the gate network with a dimension d multiply big M.
Mhm.
D, as I mentioned, it's like our dimensionality of each patch, and big M, it's number of experts. And in general, this formula says that m-dimensional vector where each component corresponds to the score for the some specific m small m expert, because our small m is like a subset of the big M dimensional vectors because it's like all our agents. Small m, it's one of the agents. Yeah, it's kind of confusing, but the
No, no,
purpose, because
M is the total number of experts, and T sub x is a subset
oh yeah, my bad.
of M integers, right? From
Yeah,
one to n.
yeah, you're right.
And the
So
small m is a element in that subset.
yeah, h from x by theta represents the scores that the gating network assigns to each expert before our softmax. Um, as you mentioned, T of x is a subset of M. It's set of the experts
Mhm.
which we can use for some specific tests. Um, the formula over here, it's root gateway values. We have HM from x by theta. It's the score for the M expert derived from the gating network. Um, soft, um, as I mentioned, we have a softmax. Um, softmax ensures that um, Tm from x by theta lies between 0 and 1, and sum of all p's values equals to 1, making them valid probabilities. Um,
Well, actually, I have a question here because yes, the formula below tells us that if you add all pi's over all m, small m, then you'll get one. So they can be interpreted like probabilities. But then in the formula above, you actually only sum over subset of m, capital M integers. And so it is a weighted average, but it is now this sum, if we just get rid of this sum f sub m, the sum wouldn't be one; it would be less than one. So
yes.
so either there's something I don't understand, or maybe in the softmax below, you should have a sum over also t sub x subset. But maybe there is some meaning to why the sum above goes over subset and the sum below goes over all integers. So not clear.
I think actually the conversion to the probability uh, it's happening over here. But as you mentioned, yeah, if we get rid of some of f's, it's gonna be actually less than none. Yeah.
Yeah, but maybe it's
Um,
not important because you're only, T sub x only has experts which give you larger probabilities. And then the formula above for f is just a weighted average of the outputs of all the experts. Yeah,
mhm.
maybe it's
Um,
not important difference. Yeah.
so here you can see the illustration of the mixture of expert layer. I'm gonna go through and explain how it works. We have an input X. The input data X is fed into the gate network. The input
There
may
is a
consist.
question. Okay, sorry, Artem. The rule here, if somebody has a question, they are allowed to ask. So, Vladimir,
Of
go
course.
ahead.
Hi, thanks for the presentation. So just one question. Is there a reason why the router is a linear network, or it's just that's just the way they did it?
Say again, please.
Why is
Is
router
there
a
a
linear
reason?
network? Yeah.
Why is router in this network?
No, why is it linear?
Uh, Actually, it's a good question. I assume that the router is supposed to be linear because uh
Isn't you going to
yeah,
get all nonlinearity later on in your networks? I mean, you don't need to have input. I mean, even if an input is linear, and you need nonlinearity, the network will learn it. I mean, maybe I don't
yeah.
understand.
I don't really
Yeah,
understand the
my
question,
guess
but
would have just been that with a nonlinear network, you could like route better, maybe.
Yeah, but like you input the linear signal through the router and then it goes to the network, but then within network you have all of the non-linearities you want. So and it will just
Right, but the network is already a sub-selection of experts. So the router kind of limits your.
Oh, no. You mean the output ones. Okay, so if you go back, I think that you're talking so if you go back, no, the pi is not linear.
Oh, okay, sorry. Yeah, I think it
No,
makes
pi is
sense.
not linear. Okay, and I think that's kind of the point that Artem is making, that if it was linear, then it is doing better, but not much. But you want pi actually not to be linear.
Okay, thanks.
yeah, the main point here, because in this paper they comparing linear and nonlinear performance, and they um highlight that nonlinear performance is way more effective than linear. I'm not sure that I understand your question correctly, but okay.
Yeah, I think this diagram is just confusing, at least to me. But if you look at the formula, I think that it's clear. If you go, there's FOM, it has all the non-linearities that each expert wants, and then at the end you still want to you need non-linearities to in pies, right? And so, and where are the non-linearities in pi? They're present in the softmax. Okay, that's a simple one, but also this h doesn't have to be linear, or does it? Or maybe Vladimir is right. Maybe I'm confused. Is h
Yeah,
linear?
I think I read the gating network is generally said to be linear. Um, but I think that's not quite the router.
Okay. All right. Well, fine. Let's go.
Then, then it's
Let's
minus.
see. Let's see.
Uh, yeah, so inside of gating network, we process the input, we generating scores for each expert, and we passing scores through the softmax to calculate the probabilities, like this one for routing.
Hmm.
What about router? Router uses the probabilities generated by the gate network to decide which expert should be used for the some specific task.
Hmm.
Um, there are like two common routing strategies. It's self-routing and top-one routing. I'm gonna mention them later. So in each experts, like it consists of, we have like M of experts, each of them specializing in some specific task or data clusters. When I mentioned about problem setting and preliminaries, I mentioned that um, each expert has some kind of direction or like specialization where like they're gonna be the most effective. Um, all these experts, they separate models with their own W's. Um, yeah. Um, we have weighted combination of outputs. The final output of the mixture of um, experts layer is computed by combining the outputs of the selected experts. Yeah, yeah, something like that. Another one is like our expert model. Um, Here we have um, um, outer summation. Um, these sums over J filters. Each filter contributes to the output of the expert. It's like our neurons. And this sum is inner summation. It's the sums over p patches of the input x. And each x power some power p processed by our filters, and we got a dot product of weight vector of the J filter in the nth expert and each the pth patch of the input X. Yeah, we don't know that WM has some, it's like a list of W's as the weight of matrix, as I mentioned, and yeah. For nonlinear CNNs, we consider the cubic activation function like this, which is one of the simplest nonlinear activation functions.
Hmm.
Yeah. Top one routing model I mentioned a few slides before. TOEIX, it's a set of agents which we can use for some specific task. Would be the whole expert set of M, because M, as I said before, it's all our expert, which is the case for the so-called soft routing model. However, it would be time consuming to use soft routing in deep learning. Switch routing is introduced to make the gated network sparse and save the computation time.
Okay, so then router is not linear if you use that. So then T sub X.
Yeah, because it's not discrete.
T sub X is what determines whether it's going to be used or not for your in your formula, right?
Mm-hmm. So the expert with the highest score from the gated network is selected by this formula, where HM of X by theta is like the score for the M expert, and this argmax is like index of the expert with the maximum score is selected. Like we make sure that we choose the best one. Yeah, and the next one is training algorithm. When I was talking about data, I said like that our data looks like this. It's like pair of X and Y. They train F with the gradient descent to minimize the empirical loss function. So that's our loss function. For the measure of the express model, it depends on the parameters of the gated network. It's here, and the express of it's like W. Well, is the logistic loss defined as this one? We initialize it to zero, to be zero, and initialize each entry of W0 by this. Zero initialization of the gated network is widely used in the model mixture of experts training. Instead of directly using the gradient of empirical loss to update weights, we add perturbation to the router and use the gradient of the perturbed empirical loss to update the weight. Yeah, I can talk a little bit more about this. So we initialize this gated network to zero. This is common, as I said before. Expert weights is big W. We initialized with randomly with each entry sampled independently from like a normal distribution over here. And this is our variance of the initialization.
So there is a hot discussion of nonlinearity. So maybe we should get to that whenever, Artem, you think you want to get back to the linearity and the router. Well, we should get there. People are writing something in the chat, and I think I am agreeing with them.
Let me open the chat then.
Oh, I can just read it. Well, Dan, you can. I think I agree with you, but if you can speak up and say.
Okay, yeah, sorry, I don't see where I can raise my hand, so I just thought I'd drop that in the chat since it took me a little
You
while
just
to
start
respond.
speaking, right? Just don't raise your hand. Just start talking like me.
Hey, so my comment there was that the router is linear because it sends either x times 0 or x times 1. into the experts that are receiving the inputs. Now, it also receives some information from the gating network, and how it uses that information, that is to send the input value to the correct networks, that might be nonlinear. But in terms of the actual operator itself, that the actual input, it's linear in that input. That was my observation.
Yeah, I think I'm agreeing with you and disagreeing with you at the same time. So I'm agreeing with you that there is a multiplication. So that part is, of course, linear. But to understand whether you multiply it by 0 or 1, you perform a nonlinear operation. So the whole together thing is nonlinear. And so like the right thing of saying to say it isn't linear. It isn't linear. To determine whether you'll multiply by 0 or 1, this whole process is nonlinear, and therefore I think we should not be. And then I think Diego confirmed that, kind of agreeing with what you're saying, is that linear is just a confusing term, should not be used here. The whole thing together is nonlinear, and that's the whole point. Because if it was linear, then it's not interesting at all. Okay, but thank you for the feedback.
Yeah.
And Diego, you should fix your microphone next time.
So yeah, here we discussed the perturbation and rota decision. It's like just continuing all the things that I mentioned here. So there's the results that we receive, like that they receive from their observations. The first one is about single expert performance, because the feature noise and the feature signal over here have the same strength, and it means the distributions of signal and noise are equal, and the classification function has the form of this one, where f from x power p processes each patch individually. As a result, for such setup, the test error is guaranteed to be large. Yeah, I think they received it like empirically, like from testing. So then they provide this some kind of like theorem that indicates that if the feature noise has the same strength as the feature signal, any two-layer sentence with a form this can perform well on the classification problem defined in the definition 3.1. It's a classification problem that I mentioned at the beginning of the presentation. Can be an activation function. Also shows that simple ensemble of the experts might not improve their performance because the ensemble of the two layers CNNs is still in the form of the function defined in this theorem. What I mean that if the noise range is like large as the signal, single expert struggles to distinguish between the signal and noise, and the expert cannot achieve good classification accuracy. Some generalization over here, even if multiple such experts are combined, the overall performance doesn't improve because the ensemble still follows the same functional form over here. Yeah. Another one is for...
Yeah, I don't, sorry to interrupt you. Don't want to run out of time because I have many questions to ask, but I think we don't have to go like in the deep details of every single theorem that they have. Just maybe get like main ideas, and then turn on the
it's gonna
discussion.
be, yeah, I can just mention like key techniques that they mentioned that they receive. So successful mixture of express layer needs to ensure that the router can learn the cluster central features. That's when we divide our data in clusters and divide the complex problem for classification into simpler linear classification subproblems that individual experts can compute. So basically, they proceed divide and conquer approach as you have in algorithms. They just have a big problem and divide it into like small parts and solve it separately. Main difficulty is discontinuities in routing, but you can solve it by stability by smoothing. I won't like cover these lemmas, but yeah, there is more information in the paper. Another one is like no real expert, because at the beginning of the training, the gating network is 0 and the experts are randomly initialized. It's hard for the router to learn the right features because all the experts looks like they have the same properties. Yeah, but it can be solved during your training. And the third one is expert load imbalance, and normalizing gradient descent can solve this issue. That's pretty much it.
Perfect. Thank you, Artem. Let's start asking question then.
Good morning or good afternoon. Thank you, Artem, for the presentation. One possible application of this is, can you use this concept to make a system that's resilient to failed training? One of the issues I run into in some of the models that I work on is I'll have multiple loss terms, and if I don't use human judgment to establish the right weightings between these loss terms, I can start out my training in a random state that rapidly approaches a stable solution that is a terrible solution to the problem. I'll get stuck in a local minimum. But it seems like if I had enough experts, I might train a bunch of these models and maybe 80% of them get stuck in this terrible spot. But the gating network will solve the problem for me. It will recognize which ones are terrible and therefore be sending everything to the ones that are not terrible. Does that seem like a reasonable application or an extension of this?
So your point is that you have just one specific problem that you want to solve, right? By using this mixture of the experts. If I understand you correctly, every expert has some kind of specialization or something. And for example, M case expert can solve this problem, but it will be not the best solution that you expect. And in this case, yeah.
Slightly differently, the solution can be either one that really does a good job of minimizing my losses, or one that does a lousy job of minimizing my losses. And whether I find a good solution or not depends in some way on my randomly initialized state. So
Okay.
in my hypothetical example, which is not yay hypothetical, 4 out of 5 times, my model training simply fails, or it goes to a lousy training. And that probably speaks more about me than my models, I understand. But it seems like then if I had 10 or 15 of these models, it would be very likely that one of them would have been trained well. And that led me to think, hey, perhaps as another part of the training of the gating network, where you're learning where to put these, where to send the inference requests, maybe part of that is also looking at what the actual losses are, given that all of the models, all the experts are trained with the same loss functions.
I see. So you're kind of saying like many different tries of training the model I can incorporate within a single architecture where they will just simultaneously train many experts, and then you're somehow at the end, even if one of them succeeded, you're saying that I can now use this to make sure that this is the right expert for that problem. And so the fact that it was stuck in the local minima isn't an issue.
The fact that there's some statistical chance of being
stuck in local minima,
being stuck
right?
doesn't.
But again, I mean, that's kind of probably depends on the distribution of this bad minima, right? So if you have many of them, then you will get stuck there regardless. If you have few of them, then So I mean, how is that better? Not just keep trying. The other way to get you unstuck is to, I don't know, make your mini batch smaller or make the learning rate larger, right?
There are other ways, yes, sir.
Yeah, and it's why would this be why would this be the right? So you're saying that is this the right technique to get unstuck from the local minima? And I'm not
Rather
sure.
than asking if rather than
Yeah,
asking if it's right, I recognize this may not be
it's
necessarily
a
efficient.
possible way. A
Is
possible.
it an effective way?
Yeah.
Do you think?
That could be. Yeah. But
Because
I don't think I completely understand it. But the other thing, it seems like it does very much depends on the distribution of this local minima. So for some distributions, this will work. Others won't. But here, I think it's more of not about the distribution as I understood it, but more of there's just not enough capacity in one expert to learn all of the things, like all of the clusters. It just by design, it isn't capable of doing that. There's just too much to learn. And then you're saying, okay, well, learn at least one of the cluster each, right? Or, and then if each of them succeeds in this partial work, then they all together can work effectively. I still don't understand why wouldn't you want to like incorporate all this into a signal architecture, and why is it convenient way of thinking about this as like many different experts solving? Why not come up with an architecture where you have it all together? And that I don't understand completely. At level of math, I don't understand. So that's kind of my problem.
I think some of it is just, being able to run the larger models that can handle more disparate data distributions.
That's right. And I would think
with fixed compute. Because like with DeepSeek, I think you can run like one expert or X number of experts that they're using at a single time on like I think 8 GPUs.
Mhm.
So technically you could have the big model that you don't actually load into all your GPUs at once. You run it through kind of the gating mechanism initially, and then you
Oh,
load the
I
right
see.
expert. So essentially it's kind of like a way to max out basically have a bigger model on smaller compute.
Oh, that makes sense. So you're
Yeah.
just saying that this is just not what you should do, but what you must do, given the computational constraints. That
Yeah,
that
well, there's also, I think, like just exponential like costs to training one big
Yep,
model
yep,
as your data
yep,
gets more diverse and different, uh, and like different applications and settings.
yep, yep.
So, I mean, at least that's what you can see with the large language models and scaling laws is you get
Right,
like linear improvements, but like the size of the model and the data requirements become exponential. And so at
right.
some point you're hitting a limit there.
And then there is also the other direction you can, ask a question in that direction. Let's say you have very large computational resources. Does it make sense to make a mixture of the mixture of experts, and mixture of experts, and like does it make sense to create that hierarchy, or no, or this isn't the right way to do it? Like why stop on the just mixture of experts? Why not create more layers? In
I think actually like that's probably where it's going. Because if you look at
well,
the brain, it's actually the brain is actually like a giant mixture of experts. We have like these cortical columns, and they're just like basically the building block of like brain compute. So
yeah,
uh
that's one.
yeah.
And also in social interactions, this is how we have, like, let's say we have a question in physics. You go to the physicist, and then within the physicist, there are experts who are experts in quantum mechanics, and they're
Right,
experts
right.
in the measurement problem.
Like
another
it's like a recursive,
Hierarchy,
distillation to
tree
more
hierarchy.
specialized experts. Yeah.
besides the more specialization, one of the assumptions going into this is that these are all similar networks, that these
Yep,
models, experts
yep.
each have the same architecture. But I was wondering, hey, what if these experts had different architectures, different activation functions, or taking a step up your machine learning model hierarchy, what if some of these were neural networks, but other were some decision trees and maybe some genetic algorithms?
Oh, absolutely. Yeah. So I don't think there is any restrictions. I mean, it's like in the simplest way, they are all the same for the analysis, but you're right. I mean, some of them may be transformers, the other will be CNNs, the other, who else? Yeah. So I agree.
Yeah, I
And
think the
actually,
only
then it
limitation
brings,
is it's
Mhm. Go ahead.
it works with back propagation
No,
differentiable.
I understand. But then even with the same architecture, you can ask question, does it make sense to have different distribution of initial conditions for different networks within your mixture of experts? Because given your distributions, you may be good in initial conditions. You may be good in learning different features of your data set. So there are a lot of things you can do to make the mixture more interesting. Yeah.
One part that was lost on me at first was I was under the impression that all of the models were trained on all of the data. And that kind of fits better with the having different kinds of models.
Mm-hmm.
I realized late within Artem's presentation that, in fact, each of the models is not trained on the same data. That during the training process, that the gating network is co-trained, and thus during that gating process, during the training process, only each expert is trained according to some of the data.
Yeah, that's
That
Vladimir's
was
point, right?
fascinating.
Yeah. That's Vladimir's point of that. They have restrictions, right, on computational resources on both for the activation dynamics, for learning dynamics, and for the data set that is they exposed. Yeah, that's a good point. Okay, let's see. There's some discussion in the chat. So Jacob, do you wanna say something?
Sure. Excuse me.
Okay.
Sure. Yeah, I was just thinking the gating seems ripe for like reinforcement learning methods where you have, because it seems like a problem with this is, how do you start finding which experts are valid in which cases? And it sort of randomly starts and just guesses. And finding that convergence seems pretty difficult. If you can maybe find it at all sometimes. But if you did like a actor critic sort of thing, so you have another network that is testing the expected value of some expert set, and that's feeding back into the gate to say, yeah, you're doing good. Oh no, you're going away from the target. You're getting better. It seems like you could converge more quickly.
But isn't the loss function is supposed to do exactly that, like figure out
Yeah, it's part of the loss function, I guess.
Yeah, so it's exactly what it should do. It should, you can of course have two different losses and two different that may complicate things. I think Dan was saying something about two different losses, although I'm not sure that was his.
My thoughts on the different losses were related in part to training on all of the data and using the loss on the collection of data. So typically, the problems that I've been working on are in the physics-informed neural networks or governing equation-informed neural networks, wherein when you express your equations in a homogenized form, the output for any value input, the loss, the output should be 0. And therefore, you can use any input. You don't have a limited set of input data, so you generally use random inputs. When you have a model that doesn't train well, say just for comparison's sake, a model trains well and you're getting down to 10 to the minus 4 loss in whatever units you might have. And one of your models doesn't train well and it's got a loss of 10 to the plus 2. So you got a 6 order magnitude difference there. Hey, can't I use that as an indicator as to whether I should be sending this model an inference at all? That was detecting poorly trained models. And by the way, one of the reasons for poorly trained models is not just because Dan can't write good models. Sometimes it's because I have multiple governing equations that are literally conflicting. That will cause large losses. So if you are setting up a problem using governing equation-informed neural networks, if you're setting up a problem that doesn't have a solution, your loss should always end up much higher than if you're setting up a problem that does have solutions. So if all of my models don't train, that might be a good indication that my problem has no solution.
No good solution. But it will find some solution, right? It may
It
not
will
be.
it will always give you an output.
Right, exactly.
You have to remember to look at the loss to determine if
But,
it's a valid output or not.
Good or bad is subjective, right? So, I mean, sometimes you get a loss that looks very good, but then you find out that you can do much, much better with little constraints on the network. But yeah, that makes sense. Okay, other questions, comments?
Yeah, I think for the secondary loss, like usually they have an auxiliary loss on the gating mechanism.
Mm-hmm.
So that basically what it does is kind of forces the gating mechanism to evenly pick between the experts, so that you don't like go into a case scenario where you're picking only on one expert always.
Well, but then you have to add it to the actual. I mean, it's just another term in the loss function.
Yeah.
So yeah, I mean, there's many other
Yeah,
terms.
it's kind of like a penalty, basically. Yeah.
Yeah, so I mean, I'm sure they have like L2 regularization and other things, but yeah, that's a good point. You have to add some kind of term to decide when to switch between experts and when to adjust your routing, right? I guess. Because router is kind of it's discrete, right? It's either like puts 0 or 1 to the input according to what Dan said. Yeah.
Yes, I think it selects just one network.
Yeah, so it's a discrete. So it's like where we have this problem now of not having a continuous, but rather discontinuous jump in the loss when you change from 0 to 1. So you cannot really do a gradient descent on that.
Vladimir, I think one of the other points that was settled to me at first was the router doesn't have to choose only one. It can choose to send that input to a collection of experts.
Oh, that's what it does, right? T sub x. Yeah, no,
Yeah,
it's
yeah.
no, of course. But again, it still has to choose to which to send and which not to send. And so that is a
And there will be
decision.
discontinuity
Yeah,
when
and
it
there's
chooses suddenly to not send it to
right, and
expert
so
number 7.
so that's kind of that discontinuity is not something you have to worry about. Okay, well, that's good. That was a very interesting discussion. Let's see if there are any other thoughts.
Thank you.
Well, thanks everyone for coming, and I'll see you all next week. Thanks.